This is the method of differences. It's part of Core Pure 2, which is GCE A-level for further maths. You should already be familiar with the series, and we want to, for example, sum from r equals 1 to n r cubed, and we'd like a shortcut. I'll begin by saying we already know what the answer is. The answer is given in the formula book, and it says it's a quarter n squared, n plus 1 squared. But where does that come from? How do we know that to be the case? Let's begin by trying to expand the sum from r equals 1 to n of r cubed. I know the sum from r equals 1 to n of r cubed is 1 cubed plus 2 cubed plus 3 cubed plus, and I miss a bunch out, plus n minus 1 cubed plus n cubed. Now I hope you'll agree it's not at all obvious how I'm going to get from that to that. Yeah, nice succinct statement about what the sum is. How does this get to that? The answer is it doesn't get there very easily. The method of differences is a trick that allows us to get there. And it relies upon, first of all, being able to express this sum of r cubed as something that involves one term minus another term. Let's explain that a bit further. So for r cubed, it relies upon this rather unlikely identity that 4r cubed is identical to r squared times r plus 1 squared minus r minus 1 squared times r squared. So let's show that's true to start with. So we'll start with the right-hand side. The right-hand side is, expand this out, r squared times r squared plus 2r plus 1 minus r squared times r squared minus 2r plus 1, which is identical to r squared times r squared plus 2r plus 1 minus r squared minus 2r plus 1, which is identical to r squared times r squared minus r squared disappears, 2r minus 2r, which is 4r, 1 minus 1 disappears, which is identical to 4r cubed, which is identical to the left-hand side. So we've done that bit. QED. We have demonstrated that which was to be demonstrated. The next step, use that to find the sum of r cubed. Well, the sum of r cubed from r equals 1 to n is the same as the sum of 4r cubed, but multiplied by a quarter, from r equals 1 to n. But that's the sum, given that we've just demonstrated that 4r cubed is this up here, the sum from r equals 1 to n of r squared, r plus 1 squared, minus r minus 1 squared, r squared. That's all inside the sum, and that's 1/4. So the sum of r cubed is 1/4 times the sum of this. Now this is where the trick comes in. If we call this the right-hand side, g of r, then I can say g of 1 equals 1 squared, 1 plus 1 is 2 squared, minus 1 minus 1, 0 squared, 1 squared. G of 2 is 2 squared times 3 squared, minus 2 minus 1, which is 1 squared, 2 squared. G of 3 is 3 squared times 4 squared minus 2 squared times 3 squared. And notice, this one here and this one here cancel out. This one here cancel out. We do some downward ellipsis here, downward ellipsis here. We'll move on to the one before last, the g of n minus 1, which is n minus 1 squared times n squared minus n minus 2 squared times n minus 1 squared. And g of n is n squared times n plus 1 squared minus n minus 1 squared times n squared. Now, if we look term by term, we'll find that the sum from r equals 1 to n of g of r equals this is going to cancel, this is going to cancel, this is going to cancel, this one here is going to cancel. These two are going to cancel, and I'm left with n squared times n plus 1 squared. The only one left up here, minus 0. But that implies that the sum from r equals 1 to n of r cubed equals a quarter times the sum from r equals 1 to n of g of r equals a quarter times n squared, n plus 1 squared. The trick was simply by expressing it as a term in r and r plus 1, take away a term in r minus 1 and r, they would disappear term by term. That's essentially what the method of differences is about. In general, you will be told how you need to express it as a term minus a term, and then you simply need to implement it. Show that 1 over r times r plus 1 is identical to 1 over r minus 1 over r plus 1. Easier probably to start from the right-hand side. Bring these together, r plus 1 minus r over r plus 1, which is identical to 1 over r plus 1, which is identical to the left-hand side. So that's that bit done. Now we use that fact to find the sum from r equals 1 to n of 1 over r plus 1. Now notice we've just managed to express 1 over r times r plus 1 in the form of something that involves r subtracting something that involves r plus 1. That's very promising. We have an r and subtracting r plus 1, then we can expect term by term things will disappear. That equals the sum from r equals 1 to n of 1 over r minus 1 over r plus 1. And now for brevity again, we'll just write that as sum from r equals 1 to n of g of r. Now term by term, g of 1. 1 over 1 minus 1 over 2. G of 2. 1 over 2 minus 1 over 3. G of 3. 1 over 3 minus 1 over 4. And we can see already the pattern. This one and this one cancel each other out. This one cancel each other out. And it continues down through the sequence. So we'll put ellipsis here to indicate we carry on. We'll go straight to the one before last. G of n minus 1 is 1 over n minus 1 minus 1 over n. And g of n, 1 over n minus 1 over n plus 1. What do we get from this then? Looking at these cancellings, we say this and this, this and this, this and this, all the way down, including that one. So we say that the sum from r equals 1 to n of g of r is 1, what's that term there that's left behind, minus 1 over n plus 1. And we just tidy that as necessary. So let's get that over the same denominator. That equals n plus 1 minus 1 over n plus 1, which equals n over n plus 1. Then going back to the original problem, we wanted to work out what the sum of 1 over r plus 1 is. So we have the sum of 1 over r plus 1, from r equals 1 to n is n over n plus 1. So that example gave us at the beginning that 1 over r times r plus 1 is 1 over r minus 1 over r plus 1. They won't always be quite that helpful, but they'll often be of that type. So here's one. Find this. Now they haven't told us what we're going to do here, but that looks very much like we're going to use partial fractions. 1 over 4r squared minus 1 is the same as the sum from r equals 1 to n of 1 over 2r squared minus 1 squared. So we're going to rewrite this as 2r plus 1, 2r minus 1, difference of 2 squares. So let's do that. 1 over 4r squared minus 1 is identical to a over 2r plus 1 plus b over 2r minus 1. But that's the same as a times 2r minus 1 plus b times 2r plus 1 over 4r squared minus 1. That implies, 1 is a times 2r minus 1 plus b times 2r plus 1, r equals a half. 1 equals 2 times a half is 1, minus 1 is 0. So b times 2 times a half is 1, plus 1 is 2. That implies B equals a half. Then let R equal minus a half. 1 equals A times 2 times minus a half is minus 1. Minus 1 is minus 2. 2 times minus a half is minus 1, plus 1 is 0. So that implies that A equals 1 is minus 2A, A is minus a half. So the sum from R equals 1 to N of 1 over 4R squared minus 1 is the same as the sum from R equals 1 to N of minus a half over 2R plus 1 plus a half over 2R minus 1. I'd rather bring this half to the outside. Is the same as a half times the sum, I should put brackets in here, sorry. A half times the sum from R equals 1 to N. Let's switch these around so I've got my minus in between them rather than at the beginning here. 1 over 2R minus 1 minus 1 over 2R plus 1. Quick look at this, we're actually separated not by one term here, but by two terms, 2R minus 1 and 2R plus 1. You can certainly see it looks like what's going to happen if we list our terms out is that terms will start cancelling each other out. Let's call this a half times the sum from R equals 1 to N of G of R. So I can talk about it more easily. Let's begin with 1. G of 1 is 1 over 2 minus 1 minus 1 over 2 plus 1. G of 2. 1 over 4 minus 1 minus 1 over 4 plus 1, 5. G of 3. 1 over 5 minus 1 over 7. That's quite nice. Let's miss some out. G of n minus 1, 1 over 2 times n minus 1, minus 1, minus 1 over 2 times n minus 1 plus 1. And G of n is 1 over 2n minus 1 inside a bracket, sorry. No, my apologies, wrong. It's 2n minus 1 minus 1 over 2n plus 1. This one cancels, this one cancels, this one cancels, and they keep cancelling all the way down. Looking at this one here, you might think that doesn't look quite the same, but it's 2n minus 2 plus 1, which is 2n minus 1. And this one here is 2n minus 1. So the sum from R equals 1 to n of G of R is this term here, 1, minus this term here, 1 over 2n plus 1, which equals 2n plus 1 minus 1 over 2n plus 1, which equals 2n over 2n plus 1. And we'll go back up here and see that we actually wanted the sum from r equals 1 to n of 1 over 4r squared minus 1, which is a half times the sum from r equals 1 to n g of r, which equals a half of that, n over 2n plus 1. Okay, I think that's enough of an example for you. Can I recommend that you move on to exercise 2a, and I suggest you do all of the questions in there. In my copy, question 7 has a mistake in a failure to put brackets around the two parts of the denominator, and question 8 has a mistake in, again, failing to put brackets around the two parts of the denominator. You'll notice that when you get there. Best of luck.